In this video, we are going to review the different forms of mechanical work. The first one that we covered in class was the work due to a force that is applied to an object. The first case, the force is in the direction of the displacement. So work is defined as force multiplied by the displacement. If the force is at an angle theta, then the work is defined as the force in vector form dot product the distance in vector form. If we have a trajectory that is curved, then we have to compute the work at every ds interval as f dot ds and integrate over the whole curve. So that integral, it will be depending on the path that we choose. So the total work from 1 to 2 is equal to the integral through the path that we choose from 1 to 2, or f dot ds. In the case of the shaft, so we have rotatory movement, and the work or the differential of work is defined in terms of the torque multiplied by the theta. To obtain the power, we divide by the theta, so we have torque multiplied by the theta dt, which is omega, the angular velocity. So remember that the dimensions of the angular velocity are radians per second, and so power is, in terms of the torque, Newton meters, and the angular velocity, the units are radians per second. So the radians do not appear in the total dimensions. Okay. These are some examples of shaft work, and we have it in almost every machine that we have. So in the case of a boat, a big boat, it has an engine, and the engine is producing a work that moves the propeller of the boat. The second example that we have is an actual bicycle. So when the force is applied in the pedals, like in here, so it will produce a torque that is transmitted by the change, and that torque is transmitted to the back wheel, and then it's converted into a force that the road exert over the wheel, and then we move in the forward direction. And the second example that we have is a car. So we have the motor that is converting the fuel energy into torque, and that torque is going to be converted into a force in the wheels that makes the car to move in the forward direction. So in this example, the car transmission shaft is rotating at 400 rpm, and a torque of 200 newton meters is applied. So the question is, what is the power transfer to the wheels by the motor? So the power is given by the torque multiplied by the angular velocity. So in this case, what we have is that the torque is 200 newton meters multiplied by the angular velocity, but the angular velocity is given in rpms, so we have to convert it into radians per second. So this is 4,000 revolutions per minute, so that's rpm, and then we need to multiply by 1 revolution, so divide by 1 revolution, which is equal to 2 pi radians, and then we have to convert the minutes into seconds. So multiply by 1 conveniently, so 1 minute divided by 60 seconds. So when we do, the simplifications, minutes and minutes cancel, revolution cancel, and the final result is in Newton meters per second. So by using a calculator we can find that the torque in the shaft is equal to 83,775 watts, which we can convert into horsepower and is equivalent to 112.34 horsepower. The third type of work is spring work. Let's suppose that we have a spring whose original rest position is this one. Then we are going to apply a force, and so the spring will move from this position to this position. Now to compute the work, we can do it by steps. So we are going to consider a differential of movement dx, of displacement, and so the differential of work is equal to the force dot product dx. So the force is constant and dx is increasing. Now the force in a spring is given by k multiplied by x, where k is the spring constant. Okay, so if we replace this value in the force, we obtain that dw, the differential of work, is equal to kx dot product dx. That dot product is a standard product because the force and the displacements are in the same direction. Now if we want to compute the total work from this position to the final position, we will need to integrate from positions 1 to 2. This is what we do here. So the integral of the work from 1 to 2 is equal to the integral of kx dx from 1 to 2. So that integral of kx is equal to, well, k is a constant, so it came out of the integral, and the integral of x is x squared over 2. Evaluated at 1 and 2 is x2 squared minus x1 squared. So that's the work due to the spring. Now, the fourth and probably most important case for this class is the work done by a fluid, and can be expansion and compression work. Now let's suppose that we have a cylinder. Let's consider the cylinder is originally in this position and is filled with some gas on liquid and is under pressure, so the pressure will be applied over the surface of the cylinder and it will make it move from x1 to x2 position. So that's the total displacement. Again, we are going to find out the work by steps. So the differential of work is equal to the force that is applying the pressure over the piston multiplied by dx. But we know that the force is equal to the pressure multiplied by the area and multiplied by dx. Now area dx is equal to the differential of volume, right? So if we move from this position to this is delta x or dx, so that differential of volume will be that will be the differential of volume. So the differential of work is equal to P multiplied by the differential of volume. And again, if we want to compute the total work, we'll have to integrate in between 1 to 2. So on the left hand side, what we have is the work from 1 to 2, and in the right hand side we have the integral, and because our integrand is the differential of volume, it will be from volume 1 to volume 2 of P dV. So let's have a look in detail to this integral. So we are integrating P over dV. So P is a function of the volume. Let's make a plot here. So we have as an independent variable the volume, and as the dependent variable the pressure. So we are in a position 1 to 2, and we are moving from 1 to 2. And so what we are computing is the integral from P1 to P2. So that integral, as we remember, is the area underneath the curve. So the work done by a fluid is equal to the area under the curve of the PV diagram. So we have two particular cases. So we have the work from 1 to 2 in the case that is positive, meaning that the differential of volume is bigger than 0, so that means we move in this direction, and in this case is expansion. The volume is increasing. On the second case, we have that the work from 1 to 2 is less than 0, so in that case dV, the differential of volume, is less than 0, so it is compressing. So in the first case, so the fluid is expanding, so the fluid is releasing, is doing a work, so the work is done by the fluid. So we said that in this case is work out, because the work is done by the fluid. In the second case, that the piston is moving in that direction, is because we are applying a force in the piston, so we are doing a work on the fluid. So in the second case, in the compression, is work in. In conclusion, work is energy transfer associated with a force acting through a distance. We have different forms of work, and they include the work of a force, the electrical work, shaft work, spring work, and the most important for us, the work of a fluid. And that one in particular, the work of a fluid, could be compression or expansion, and is equal to the integral under the PV diagram of P dV.